Okay, so in this video we will be discussing another quality of the point estimators. Okay, so this quality is called consistency. Okay, so as the name suggests, by consistency we mean that every time we predict or we estimate certain population parameter, for example theta, from an estimator that is the sample statistic theta bar, we get the same value which has no or very small difference with real value theta. Okay, so by consistency we mean that every time we want to estimate certain population parameter, okay, we know that we estimate this population parameter theta from using the sample statistics. Okay, for example in real time we may calculate or estimate population mean, which is denoted by mu, from using sample mean x bar. Okay, so here this sample mean x bar is the point estimator. Okay, and population mean mu is the value that we want to estimate. Okay, that is the population parameter. Okay, and this is the sample statistics, sample mean x bar. Okay, so consistency is another quality of the point estimators. Okay, so let us first define it formally. Okay, so by definition we have the sample statistic theta bar is consistent estimator of population parameter theta if and only if for each c greater than 0 limit n tends to infinity, the sample size is very large, the probability of the difference between these sample parameter and the population parameter is less than c is equal to 1. Okay, what is c? C is the arbitrary constant and has very small value. Okay, so what this definition means? This definition means that when n is sufficiently large, okay, n is very large, the probability of the difference between the theta bar, which is the sample statistics, and theta, which is the population parameter, is less than c, where c is an arbitrary constant, is equal to 1. Okay, it means that we are confident, okay, 100%, because the probability is 1, that the difference between the estimator, which is the sample statistics, and the population parameter theta that we want to estimate is equal to 0 or is less than c, okay, where c is very small arbitrary constant. Okay, so when this difference is less than c, for c is very small, and the probability of this difference less than c is equal to 1, which means that we are 100% confident, okay, then this estimator is called the consistent estimator. Okay, so it literally means that every time we make an estimate, we get the real population value. There is no difference, or the difference is very, very small. Okay, the value that we estimate and the real parameter value has either very, very small difference or no difference at all. Then the estimator is called the consistent estimator, theta bar. Okay, and this property, okay, this property, we will talk about this property, which says that limit tends to infinity. It means that the sample size from which we are taking the statistics to predict or estimate the population parameter, n, is very, very large. Okay, such large that it is tending to be infinite. Okay, it is nearer to infinite. Okay, the probability of theta bar minus theta less than c is equal to 1. This equation is actually called the convergence of probability. Why this conversion? Convergence means that it is collecting to a single point. And which is that point? The point is that the probability becomes 1. Okay, we are getting 100% sure at that point. So the probabilities, okay, we know that the probability is between something between 0 and 1. Okay, so for this, the probability ends at this position. It converges to this position. Okay, so it means that if we make the sample size n large enough, okay, the probability of these differences, okay, it becomes either very, very small, okay, such small that it is less than c, where c is an arbitrary small constant. Okay, so this is the consistency property of this estimator, point estimators. Okay, okay, so by this definition we see that consistency is actually asymptotic. And by asymptotic we mean that this property is limiting. And how it is limiting? It is limiting because it is applicable only when n is sufficiently large as infinite. Okay, when the sample size is very large, then this property comes into effect. Otherwise it is not coming into effect. It means that it is not applicable, or the results that we get, before this stage, n is greater than or equal to infinite, okay, are not consistent. Okay, we may get very large errors. Okay, and the error is this thing, theta bar minus theta. Okay, bar minus theta is literally the error or the difference between the real estimate, the real population value, and the estimator sample statistics. Okay, it means that when the sample size is very large, this error is becoming very small. So when it becomes very small till it is less than c, okay, we get a consistent value after that. But before that we are not getting any consistent value. So this is actually asymptotic property. Consistency is asymptotic property. It means that this property is limiting and is it comes into effect only when n is very large, or it tends to be infinite. Okay, so based on this asymptotic property of consistency, we have a theorem. Okay, theorem 3, and this theorem states that if theta bar is an unbiased estimator of theta, which is a population parameter, then and variance of this theta bar tends to 0, becomes 0 when n tends to be infinity, or for very large sample size, then this theta bar is consistent estimator of theta, which is the population parameter. Okay, I hope you have understood this theorem. If I translate it in literal meanings, okay, it states that if we have a sample statistics theta bar, okay, and it is unbiased estimator of this theta, which is the population parameter. Okay, for example, we term this theta bar actually is equal to x bar, which is the sample mean, and theta is equal to mu, which is the population mean. So it says that the x bar is the consistent estimator of this population mean if the variance in x bar is equal to 0 for n tending to be infinity, or for very large size, very large sample size. Okay, so when this happens, Okay, then this x bar is the consistent estimator of this mu, which is the population mean. Okay, this is theorem number 3. Now we will move to an example, solved on this consistency quality of the point estimators. I will do the example in the next video. Example on consistent estimator. Okay, so this example states that we need to show that x bar is a consistent estimator of population mean mu. Okay, so we know that x bar is equal to summation of xi for I is equal to 1 up to infinity divided by n, up to n. Okay, because the total number of sample size is n. Okay, okay, this is the definition of the sample mean. This is the sample mean, and this sample mean is our estimator or sample statistic. Okay, we will use this one to calculate that it is the consistent estimator of this mean, population mean mu. Okay, so to find that it is a consistent estimator or unbiased estimator, we want to find the expected value of this x bar. Okay, so putting the value of x bar into this, we get expected value of xi okay, so we get expected value of 1 over n multiplied by the expected value of summation of xi for I is equal to 1 up to n. Okay, now this 1 over n is constant, so we will get the same value. Okay, and the expected value of this summation of xi up to n is equal to n into mu. Okay, now n will be cancelling with the other n, and we get E of x bar is equal to mu. Okay, now it shows that it is the unbiased estimator of mu. Okay, x bar is unbiased estimator of mu, and that is the basic according to theorem 3. Okay, which states that if theta bar is unbiased estimator of population parameter theta and variance of theta bar tends to be 0 for n tending to be infinity, then theta bar is the consistent parameter. So the first condition, which was that theta bar is the unbiased estimator of theta, here we have x bar as theta bar, and against theta we have mu. So the first condition is met. Now we go to the second condition, okay, which states that the variance of theta bar tends to 0 for n tending to infinity. Okay, this is the second condition. The first condition is already met, so we need to see the second condition for a consistent estimator. Now the variance of x bar, because we will replace this theta bar with x bar as we have x bar as the estimator, okay, is equal to the variance of putting the value of x bar. X bar is equal to summation of xi divided by n, okay, summation of xi for I is equal to 1 up to n divided by n. So we get variance of 1 over n into variance of summation of xi for I is equal to 1 up to n. Okay, this is constant, so variance of 1 over n will become 1 over n square, and variance of xi, it will become n standard deviation square. Okay, so this square will be cancelled with this n, so what we will get is the sigma square divided by n. This is the variance of x bar. Okay, now what was the condition? The condition is that the variance of theta bar tends to 0 for n tends to infinity. If in this, for example, we state it as a, okay, so if in a we put n is equal to infinity, so what we get? The variance of x bar is equal to sigma square divided by infinity, and anything divided by infinity is equal to 0. So what we get is the variance of x bar is equal to 0 for n is equal to infinity. So the second condition is also met. So we can state that this x bar is the consistent estimator of mu, which is the population mean. Okay, I hope you have found it useful and you understand it. Let me know if there is any problem. Thank you. Okay, in case you are wondering like how we got this variance of 1 over n as 1 over n square, so we have a scaling property which states that variance of n xi is equal to n square into variance of xi. Okay, so that is how I get 1 over n square. Okay, I got 1 over n whole square, it is equal to 1 over n square. Okay, and the variance of xi, so from the example we have that xi is equal to x1, x2, x3 up to xn. Okay, we have this, and these are identically distributed. Okay, so that is why we get the variance for 1. Okay, the variance for x1 is sigma square. Okay, so the variance for xi is equal to n times into sigma square. Okay, so this is another clarification so that you are not confused. Okay, so that is how we got these values and put over here. Okay, I will also do another example on the same consistent estimators. Okay, so in this video we will be doing the first lecture on the estimation methods or point estimation in statistics. Okay, so first of all we will explain and define the estimation. Okay, so in statistics, actually estimation is one of the widely used method to predict or estimate the value of a certain population parameter. Okay, so estimation is actually getting the value of certain population parameter like mean, mu, okay, using some sample statistics. Okay, this sample statistics may be X bar. Okay, so estimation is actually getting the value, or we can say that predicting, okay, or estimating the value of certain population parameter, okay, like the mean of a population, mu, using some of the sample statistics like X bar, which is the mean of the sample. Okay, so now in estimation we have two types of estimation that is done in statistics. Okay, the first one is the point estimation and the second one is interval estimation. Okay, we will be focusing on this first one, the point estimation. Okay, but I will explain the difference between these two. Okay, so point estimation, actually it predicts or it estimates a certain value. Okay, it estimates a certain value, okay, single value, okay, for a population parameter using the sample statistics. Okay, while the interval estimation, it estimates the range of values, okay, of certain population parameter using sample statistics. Okay, both are similar methods, but in point estimation we get a single value, but in interval estimation we get a range of values. Okay, by interval estimation, okay, the best example is the confidence interval. Okay, confidence interval, which is a value of, like, we say X bar plus minus standard deviation, okay, divided by under the root n. Okay, now this plus minus, it gives us certain range, like for example from 100 to 200. So the best estimate is that the population parameter falls between 100 and 200. Okay, so this is how the interval estimation works. But in the point estimation we get a single value for a population parameter. Okay, for example, I am considering the mean of a certain population, okay, which is mu, and I want to find or estimate the mu using the X bar for a sample that is taken from this population. Okay, So this m1 bar is equal to summation of x of I raised to power 1 for I is equal to 1 up to n divided by n. So it becomes xi for I is equal to 1 up to n divided by n. So ultimately becomes x bar. Okay, and this m2 bar is equal to summation of xi, and we have a square over here because it is the second parameter. Okay, divided by n for I is equal to 1 up to n. Okay, so these are the sample moments. Now equating the respective sample moments with the theoretical moments. Okay, so the first theoretical moment was expected value of x, which is equal to alpha beta, and it is equal to mu1 bar. Okay, so equating 1 with 1, we get alpha beta is equal to x bar, or we can say m1 is equal to x bar. Okay, so m1 bar is equal to alpha beta. This is the equation 1 that we get. Okay, now equating the second one, so for the second one we get m2 bar, which is the second sample moment, is equal to beta square into alpha plus alpha square. Okay, so m2 bar is equal to, let's open it, so it will be equal to alpha beta square plus alpha beta square on both, so it will be equal to alpha beta square plus alpha beta whole square. Okay, now alpha beta, we know that this alpha beta is equal to m1. Okay, we already derived it into equation 1. So putting this alpha beta is equal to m1 in this second one. So m2 bar is equal to alpha beta square plus m1 square, m1 bar square. Okay, and we know that alpha into beta square is equal to alpha beta multiplied by beta, and we know that m1 bar is equal to alpha beta. So replacing this alpha beta with m1 bar, so we get m2 bar is equal to alpha beta into beta plus m1 bar whole square. Now alpha beta is equal to m1 bar, so m2 bar is equal to m1 bar into beta plus m1 bar whole square. So beta is equal to m2 bar minus this m1 bar whole square will come to this direction because it is open, so we can move it. This is in multiplication, so we cannot move it directly. Okay, so we can also write it as m1 bar into beta is equal to m2 bar minus m1 bar whole square. Now moving this m1 bar into this direction, or dividing both sides by m1 bar. This m1 bar and this m1 bar, we cancel each other out. Okay, and beta estimate is equal to m2 bar minus m1 bar whole square divided by m1 bar. So this is the equation for the beta. Okay, for alpha, we know that m1 bar is equal to alpha into beta, so alpha estimate is equal to m1 bar divided by beta. Okay, so this is the estimate for the first parameter, this is the estimate for the second parameter. Okay, we can also put the original values of the m1 and m2. Okay, so we know that m1 is equal to x bar and m2 is equal to summation of xi square divided by n for I is equal to 1 up to n. Okay, so we can also put these values and get some equation. Okay, if you put these values, then this alpha bar, okay, this estimate, it will be equal to nx bar square divided by summation of xi minus x bar whole square for I is equal to 1 up to n, and the beta estimate, it will be equal to summation of xi minus x bar whole square for I is equal to 1 up to n divided by nx bar. Okay, we can also write it in this form, we can also write it in this form. Both are equivalent. Okay, so in this video we will be doing the example 14, which is on page 300, and it is related to the method of moment estimator, MME. Okay, so it says that given a random sample of size n, okay, so the sample size is n, it is general, okay, and it has a gamma distribution, so the x belongs to the gamma distribution with these two parameters alpha and beta. Now they want us to use the method of moments, okay, to find the estimates of parameters alpha and beta using the method of moments estimates, MME. Okay, so let's solve it. Okay, now remember the 4 steps. Okay, the step 1 is to compute the theoretical. Okay, compute theoretical moments, but this is actually step 2. Step 1 is to identify the parameter to estimate. Okay, identify parameters to be estimated. This step is already done by the question, and we want to know about the parameter alpha and beta. Okay, so we will start with the computing the theoretical moments using the probability distribution, and the probability distribution over here is gamma distribution. So as x belongs to the gamma with the parameters alpha and beta, okay, we know that the expected value of x in the gamma distribution is equal to alpha beta. Okay, and the expected value of x square needs to be found. Okay, now we know that the variance of x is equal to expected value of x square plus expected value of x whole square. Okay, now expected value of x is equal to alpha beta. Okay, and we know that the variance of x is equal to alpha into beta square for gamma distribution. Okay, so putting the value of variance of x and e of x in this equation, let's suppose we name it A. Okay, so putting value of variance of x and e of x in A, what we get is, we get alpha beta square is equal to e of x square plus alpha beta whole square. Now e of x square is equal to, okay, let's move this thing to this opposite side. Okay, so it is equal to alpha beta square. This is positive over here, so it will become negative on when move on the other side, alpha beta whole square. Okay, so we can have like alpha beta square minus alpha square beta square. Now beta square is common between these two, so let's take beta square as common and we get alpha minus alpha square. It is the value of e raised to power e of expected value of x square. Okay, I have made one mistake over here. The thing is that this is negative. Okay, e of x square minus e of x whole square. Okay, this is minus, so when it comes, to the other direction, it becomes positive when it moves to this direction, so it will be plus. Okay, it will be plus, and this will be also plus alpha square. So this is now the correct exact value of e of x square. Okay, now we have the theoretical moments for both the parameters. Okay, now we will find the sample moments. Okay, computing sample moments, which is denoted by m1 prime and m2 prime. As there are two, so these are the sample moments. Okay, so this m1 bar is equal to summation of x of I raised to power 1 for I is equal to 1 up to n divided by n. So it becomes xi. In this video we will be doing the different methods of estimating estimators for a single population parameter theta. Okay, so the first method is the method of moments. Estimator. Okay, this method is also shortcut written as MME. Okay, so we know that we have a single population parameter theta. Okay, now this parameter has a number of different estimators, which means that a number of different methods can be applied to estimate the population parameter theta. Okay, so the basic methods, okay, or main methods are two basically. okay, the method of moment estimator, MME, and the maximum likelihood estimator. Which is MLE. Okay, so these are the two main methods. Today we will be doing this one, okay, the method of moment estimator. Now what is an MME? Okay, it is a statistical method or technique used to estimate the parameters of a probability distribution, okay, by equating sample moments to the population moments. Okay, the sample moments are denoted by MK bar, while the population moments are denoted by mu K bar. Okay, so the method of moment estimate, okay, MME, is actually a statistical technique used to estimate the different parameters of a probability distribution. Okay, we have probability distribution over here. To knowing the probability distribution is very important. It is the basic thing. Okay, after knowing the probability distribution, we have the sample moments for that probability distribution. Okay, and then we have the population moments. Okay, then we equate these sample moments to the population moments and we get some value for the estimate used. Now coming to why to use this MME method. So the first thing is that it provides simple and intuitive parameter estimates. Number second is that it works well with many distributions. Remember that we discussed probability distribution over here, which is the main part of this method. Okay, so it works very well with many distributions. Okay, and the third thing is that it requires low calculations or computations. Okay, so these are the three things to know, like why we use this particular method. This is the points behind this method. Now the thing is that we want to know that what is the sample moment. Okay, after the sample moments, we must define the sample moments, that what is sample moment, so we can understand the theory behind this whole process. Okay, now a moment of a probability distribution is the expected value of a power of the random variable. So the kth sample moment, according to this definition, will be, for population, it will be mu k, and for the sample it will be equal to mk bar. Okay, so I can write it over here as this sample moment mk bar, it is equal to the mean of kth power of observations in sample. Okay, it means that mk bar is equal to 1 over n into summation of xi raised to the power k. Okay, and k is equal to 1, 2, 3 up to r, where r is the total number of the estimators. Okay, so the sample moments actually is the mean or average of the observations x1, x2, x3 up to xn to the power of k. So mk bar is equal to 1 over summation of xi raised to power k, for I is equal to 1 up to n, and k is equal to 1, 2, 3 up to r, which is the number of parameters that we want to make the estimate of. Okay, so this is the basic concept of the sample moment. Okay, now the step-by-step guide on how to do the sample moments estimating, the method of moment estimate using the sample moments. Okay, so the first thing is to identify the parameters which you want to estimate. Okay, after identifying the parameters, we need to compute the theoretical moments using the probability distribution. Okay, why this probability distribution is important? Because for each probability distribution we will have a different computation of these theoretical moments. Okay, so that is why probability distribution is a must. Okay, after that we compute the sample moments. Okay, the theoretical moments are for the population parameters, okay, and the sample moments are for the sample parameters. Okay, and this is from the observed data. And the fourth thing is to equate it and solve for the unknown parameters. Okay, that is mu k bar is equal to m k bar. It will give us the unknown parameters. So now I will do an example. And I will solve it so you can see how we can do it in real time. Okay, this is example 13 in the book, and it is on the page number 300. Okay, it says that given a random sample of size n from uniform distribution. Okay, uniform distribution. Remember, we have this sample from a uniform distribution, and this uniform distribution has the parameter beta is equal to 1. Okay, one parameter is given to us, which is beta, and its value is 1. Now it wants us to use the MME to obtain formula for estimating the second parameter 13 in the book, and it is on the page number 300. Okay, it says that given a random sample of size n from uniform distribution. Okay, uniform distribution. Remember, we have this sample from a uniform distribution, and this uniform distribution has the parameter beta is equal to 1. Okay, one parameter is given to us, which is beta, and its value is 1. Now it wants us to use the MME to obtain formula for estimating the second parameter, which is alpha. Okay, now the first thing is to identify the parameter. Okay, so we have alpha identified as the parameter to be estimated. Then the second term is the second thing in this question is to compute the theoretical moments using the probability distribution. Okay, so the theoretical moment for this is equal to alpha plus beta divided by 2. For uniform distribution, the mean can be found using this formula. This is the theoretical moment for this distribution. Because it is uniform distribution, okay, we have two parameters, A and B, okay, also known as alpha and beta. Okay, so the mean of this is equal to alpha plus beta divided by 2, or A plus B divided by 2 for uniform distribution. So this is the theoretical moment for this probability distribution. Okay, now the third thing is to compute the sample moment, okay, which is mk bar. We need to find this thing. Okay, now this thing alpha plus beta divided by 2, this corresponds to the sample mean. Okay, this is the population mean. Okay, and this is mk bar is sample mean. So mk bar is equal to x bar, or 1 over n into summation of xi raised to power k for I is equal to 1 up to n, and this corresponds to x bar. So now we have the sample moment, we have the theoretical population moment. Okay, now the fourth thing to do is to solve for the unknown parameters by equating uk bar is equal to mk bar. Now uk bar is equal to alpha plus beta divided by 2, and mk bar is equal to x bar. Okay, so we have beta is equal to 1 as given in the question. Okay, we have beta is equal to 1 already given, so we need to put the value of beta is equal to 1. What we get is, we get alpha plus 1 divided by 2 is equal to x bar. We need to solve it for alpha. Okay, so these two will be supplied to the other side, so we will get alpha plus 1 is equal to 2x bar. Now alpha is equal to 2x bar minus 1. This is the equation for this alpha estimate. Okay, if we have the sample mean, we can easily calculate the alpha for beta is equal to 1. So this is the exact formula that we needed to find in this particular question. So that is how we solve these problems. This is the complete guide step by step to calculate this.